All right, sample problem 9. A buffer is made by adding 15 grams of ammonia and 55 grams of ammonium chloride to enough water to make 1 liter of solution. The Kb for the ammonia is given as 1.8 times 10 to the minus 5. And we're going to do what we generally do for these buffer problems. First, find the pH of the buffer. Then find the pH of the buffer after the addition of a strong acid. Then find the pH of the buffer after the addition of a strong base. The only thing that makes this example a little different than previous examples is that rather than being given the amounts in moles, we're given the amounts in grams, and we're going to have to find the amount in moles before we do our neutralization reaction. All right, so let's first find the concentration of the ammonia. We're given 15 grams. Ammonia has a molar mass of 17 grams per mole. In 1 liter, that's an initial concentration of 0.882 molar. Do the same thing for the ammonium chloride. We start with 55 grams. It has a molar mass of 53.5 grams per mole. In a 1 liter solution, that's a concentration of 1.03 molar. We can also find the Ka so that we can find the pH using the Henderson-Hasselbalch equation. Remember that Henderson-Hasselbalch is pH is equal to pKa. So if we're given the Kb value, we have to find the Ka. Just remember this idea that Ka times Kb is equal to 1 times 10 to the minus 14. Okay, so we were given Kb for the ammonia. We can find Ka just through a little bit of algebra here, and we get that Ka is 5.56 times 10 to the minus 10. Okay, so now it's pretty straightforward to find the pH of the buffered solution. It's the minus log of the Ka, or minus log of 5.56 times 10 to the minus 10, plus the log of the concentration of the base over the concentration of the acid. So the base here is the ammonia, 0.882, over the concentration of the conjugate acid, the NH4 plus, is 1.02. So we get an initial pH of 9.19. And that's as expected here, right? We have a buffer solution that has a base and its conjugate acid. So we would expect to see a pH greater than 7 here. Okay, so there's our original pH, 9.19. What happens when we add a strong acid? So the first thing we do here is in our neutralization chart, I do want to just remind us that this is amounts in moles, but it's the same as the concentration because we're talking about a volume of 1 liter. So we start with our initial amounts before any neutralization occurs. 0.882 moles of base. This is how much of the acid we were told in part B was added on the previous slide, 0.013 moles. And our initial amount of moles of the acid, 1.02 moles. A little bit of rounding difference if we get 1.02 or 1.03. Then what is our assumption? Our assumption is that all of the strong acid added is neutralized by the base. So that's why here in our table during neutralization we see that the strong acid is completely used up, minus 0.013 moles, so that we end up with 0 moles of the strong acid. The strong acid is neutralized by the base, so it is also used up as it neutralizes. So we have minus 0.013. So after neutralization, we have 0.869 moles per liter in 1 liter of base. And when the base neutralizes the acid, right, we have a reaction that looks a little something like this, right, where we get this NH4 plus. We're creating our conjugate acid there, so we're increasing the amount of the conjugate acid by that same amount in the neutralization. So we have a final amount of 1.033 of our acid. Then just use the Henderson-Hasselbalch equation to find the pH after neutralization. So the minus log of the Ka, again, same as in part A, plus the log of the new concentration of the base, 0.869, over the new concentration of the acid, 1.033, and we get a pH of 9.18, almost exactly the same as our pH with just the buffer solution. All right, let's continue with part C of sample problem number 9. We're asked to find the pH after 0.015 moles of strong base is added to the buffer. So that strong base will be neutralized by the acid that's in the buffer solution, the ammonium NH4+. Okay, so we start with our initial amounts of ammonium and ammonia, 1.02 moles, 0.882 moles, and how much strong base is added, 0.015 moles. Again, we use up all of the strong base hydroxide ions, so we're left with none. As it's neutralized, the NH4+ also gets used up, and in doing so, we generate excess NH3 in order to calculate our new amounts of NH4+ and NH3. So we have 1.005 I didn't subtract there, 1.005 moles of NH4+ and 0.897 moles of NH3 per liter, gives us a concentration there equal to the number of moles. So we find the pH equal to the pKa, or the minus log of 6.67 times 10 to the minus 10th. Remember, this is our Ka value that we calculated back in part A, plus the log of the new concentration of the base, 0.897, over the acid, 1.005, to get a new pH of 9.21. Our original pH was 9.19, so very little change in the pH after the addition of the strong base.